Okay, so the next talk is by Jürgen Blum, who tells us about the growth of macroscopic bodies in protoplanetary disks, experimental evidences and their implications.
Yeah, good morning, everybody. Welcome. Nature is not simple. We heard that yesterday in Doug Lynn's talk, I believe, and Stuart Weidenschilling showed us his model of how he thinks planetesimals grow, and this model is very complex already. So I want you to take home two things. One thing is it's even more complex than that. And the second thing is that if you want to solve the problem, you have to work together between theory and experiments. It only works that way. Now it's getting complex, so if you want to leave, you may. Okay, I want to try to show you how complex the things are in the next 45, 50, 60, 70 minutes or so. And I hope I can convince you that we have some solution, but however, unfortunately not the solution to forming planetesimals. So the solution is kind of a negative one. And I'm starting to lose my confidence that planetesimals form via coagulation. Okay, so my talk is divided into three parts: experiments, theory, and getting things together, or learning from theory in order to make new experiments. So let's start with the experiments. We do experiments in the lab and sometimes under microgravity conditions, but a warning, we do experiments mostly with one particle type. This is silicon dioxide, SiO2, amorphous. It actually does not matter too much what material it is, unless it's ice maybe, but we mostly use monodispersed spherical particles of a radius of 0.75 microns. So these are micron-sized spherical monodispersed grains. You see an electron micrograph picture here. I believe that all the results I will be talking about do depend on the grain size, maybe on the grain shape, maybe on the grain size distribution, but not so much on the material. So this is a plot that Gerhard Wurm and I put together when we wrote our review about 2 years ago, and things have changed dramatically since then. And this is the monomer grain size, and this is kind of a sticking threshold velocity. And you can see if you go from nanometer to microns to hundreds of microns, this changes over orders of magnitude. So I will be talking about this size, and we heard yesterday that meteorites consist of basically micron-sized particles. This is where the mass is. So this is, I believe that we are around here. But a warning, this is only one material, one grain size, one shape, and this may change with all these parameters if you change those. So we have two recent papers submitted to ANA, and I will be talking about those two papers. Paper 1 is an experimental one, and paper 2 is a theoretical one. This is a collaboration between the people from my institute and the people at the MPIA in Heidelberg, and it worked out quite nicely, as you will see. So paper 1. This paper reviewed all the 19 different experiments that we have our hands on. The references are here. You are not intended to read all this. And I asked Carsten to plot all the experiments in a very simple parameter space. This is the velocity where the experiments happened, and this is the mass of the grains that collided. Grains consisting of micron-sized particles again. And it's not well covered here. However, this picture is too simple. It is a two-parameter picture, velocity and mass. And looking into all these 19 experiments told us that's not sufficient. We do need at least two more parameters. This is porosity and the ratio of the mass of the two colliding bodies. Stuart told us that the small things collide with the large ones. So is that the same as if I do experiments with two aggregates of the same size? Actually, it is not. So we invented two new parameters, the porosity, and we did it, and the mass ratio, and we did it in a binary way. And this is sketched here. So whenever things are dark gray, these are porous, these are non-porous, dense, packed materials, and the white ones are porous, so a little p and a little c. And the mass ratio, we divided into two, also binary parameter space, equal size collision, so one aggregate collides with another one of the same mass, and different size, very different. So one thing is much bigger than the other. So we have altogether 8 combinations. So a small particle, a small porous particle may collide with an equal sized small particle, pp. This is that collision. A small porous may collide with a large porous. This is that collision, and so forth. So there's 8 combinations that is possible, and the little PC and CP are a little different. So this is asterisk here. So 8 combinations of porosity and mass ratio on top of the mass velocity parameter space. In our review 2 years ago, Gerhard and I showed in a diameter versus diameter plot, so this is what can collide in principle, that there's 3 regions. This is the sticking part, then there's a bouncing part, this yellowish things, and the red ones is the fragmentation. Looking deeper into all these 19 experiments showed us that this is over simplistic here. So we not only have a sticking, but we have 4 different types of sticking. I will call them S1 through S4, and I'll show you what these mean. We have also 2 types of bouncing. Bouncing is a collision where nothing really happens. However, things happen in bouncing, and I'll show you what. And 3 types of fragmentation. So we have sticking, bouncing, and fragmentation, but altogether 9 different types of those. And here they are. So it's again for equal-sized particles colliding and for different-sized particles colliding. So on the left-hand side, the equal-sized, and if there's some dash here, so this is not valid for this equal-sized particle, different-sized, and here the second column as well. So we have a simple hidden stick. I will talk about that just on the next slide, I think. Sticking by surface compaction effects, sticking by deep penetration. This is a process that Stuart just mentioned. We do have mass transfer in a fragmentation event. However, this is sticking because the bigger one gains mass. We have bouncing, just simple bouncing with a little bit compaction, and bouncing with mass transfer. We have the simple fragmentation. And if this is not equal-sized particles, we call that erosion. And we have fragmentation with mass transfer, very similar to that, but the large particle loses mass in that case. So these are the 9 different types of things that can happen. So on the right top corner, you'll always find the little pictograms, and you find all the references here. And this is what I will be talking about. Hidden stick, that's the very simple thing. 2 particles come together and they stick at the point of first contact. They hit and stick immediately by surface forces, van der Waals forces. Very, very simple. And we've done in the past 10 years or so many experiments, and all these experiments, different pictures from optical microscope, electron microscope, reconstructions, show the same thing, namely these open, fragile-looking structures, and we know that these are fractals with a fractal dimension of about 2 or a little bit below that. And fractals you may form in a hidden stick process if you start out with monodispersed spherical particles. Within one collision timescale, they form these dimers. Within another different collision timescale, they form these quadrumers. And at any time, the distribution stays quasi-monodispersed. You can show that experimentally. And if it's a hit and stick thing, no restructuring, then you form these open structures, and these are fractals. And if you have a growth like that, usually the mass versus time grows as a power law or even exponentially fast, depending on the driving relative velocities. So for Brownian motion, the power is about 2. And for relative settling, it can be faster than that. Okay, that is how it all starts. We're still at hidden stick. Hidden stick is if the relative velocities are higher than the friction can hold, so to speak, very simply, then the particles restructure. It's no longer hit and stick. And by the rolling friction, we can define a threshold in velocity for the hit and stick, and this is a typical law. Velocity of this threshold scales with a mass, reduced mass in that case, to the inverse square root. This is a typical law that will be applied in our model. And if 2 fractal particles of different masses collide, they still form a fractal, and we don't deal with fractality here, but with porosity. And the parameter that Chris Ormel invented is the enlargement parameter. And this is the volume that a fractal encompasses somehow, divided by the volume it it would have if it was compact. So this is the enlargement in volume due to its openness of fractality. And we have a mixing rule how the new enlargement parameter looks if you have the projectile and the target enlargement parameter. And it looks a bit complicated, but it's a very good fit to simulations. Okay, that's the first process. Second process is sticking through surface effects. If the velocities are bigger than the threshold I've just shown you, things can flatten out, and we use a Hertzian model describing a rather spherical particle to define a threshold velocity where this happens, up to which this happens, and this involves some macroscopic mechanical parameter which has to be measured in the lab, and some complex other values. And you see an example here. So this is a 100 micron aggregate, and this is one image, next image is here, third image is here, and there's a target, and it hits the target and sticks. And we have measured in the lab at which velocities that happens, and this matches this model more or less nicely. And so we have the second regime. It's not a hit and stick, but it's still a sticking process with some compaction. Third process is sticking by penetration. You see the particles coming in. They are highly porous, hitting an even more porous, larger aggregate. So this is a process that just happens if you have a small and a large one. Let's have a look at it again. So they hit, and they also stick, but penetrate deeply. You see the craters here. This tries to get out, but cannot get out because the binding forces are bigger than that. And in that paper we showed that this can be approximated by a lower velocity threshold, and this formula was found out by many dozen experiments on this, all happening under microgravity conditions. So by the way, this is most of what I'll show you is done under microgravity conditions. If you do this on Earth, of course, the particles will hit and stick. So you have to get rid of gravity that binds these things. So this was done in a drop tower at 10 to minus 6 Gs or something like that. So any gravity is absolutely absent in these experiments. So you can believe what you see here. Okay, another experiment done in the lab this time, but from the particle aggregate comes from the bottom and hits a target on top. And the target is, this is the gray color, is a dense target. And it happens at high velocities, and you see some fragmentation. The fragments fall down again, but against gravity, this pile sticks here. So the solid target gains some mass, and we found out in experiments that you need at least about 1 meter per second velocity. And we also follow the distribution of masses of the fragments, and we define the fragmentation strength, giving the mass of the largest fragment and the power law mass distribution of the fragments. So we can quantitatively describe at a certain velocity range for some certain porosity and mass ranges this process. Okay, those were the 4 processes that gained mass for the larger of the 2 colliding bodies. Now let's come to the bouncing cases. You see an experiment of 2 very similar sized, very porous, 85% porosity aggregates colliding, and they just bounce off. And that was known for many years that this bouncing happens, and the bouncing is relatively uninteresting. It just spreads the timescale a little bit. However, it does other things as well. We asked ourselves, where does the energy in this collision go? And earlier work has shown that the coefficient of restitution squared, this is this number as a function of impact parameter, and let's have a look at the 0 value, which is central collisions, is almost 0. So like 95% of the kinetic energy in this collision is dissipated somehow. And the question is, where does that energy go to?
Jürgen, may I stop you a second? How does the result of that bouncing changes with the angle of impact?
Actually, not so much. No. We can go back to the older work. So we lose 95% of the kinetic energy here, and at the glancing incidence, that's the 1 value, we have about 50% of the energy that goes into something else. So it's an effect, but it's not a major one. Okay, we've done an experiment to to find out what happens in bouncing. So we took a vibrating plate, a highly porous dust aggregate on top, and let it bounce thousands of times, and observed the size of the and the mass actually of the aggregate. So it started out with some like angular aggregate. We cut a piece of our high porosity dust samples that we can produce in centimeter sizes into millimeter sizes. Let it bounce a few times. Then after a few bounces, it was roundish. It lost some corners, so we forget about that. But following over hundreds to thousands of collisions, it clearly became smaller. And we measured the mass at the beginning and at the end, and calculated how the filling factor, that's the inverse of the enlargement parameter, changed with the number of collisions. So we start with about 15%, so this 85% porosity, and after a couple of thousand collisions, these things kind of saturated and were much denser. The density was 35% of the bulk density, or 65% porosity. So bouncing is important because it changes dramatically the density of the aggregates. They become compact, and the compact aggregates collides completely differently as compared to a porous aggregate. So it is an important process, besides the importance that it stretches time scales. And something else happened in these about 20,000 collisions we observed. 4 collisions did fragmentation. So this is just before the fragmenting event, and this is the next picture or next cycle, and it fragmented this and that. Again, 2 pieces, almost equal size. So we have a very, very little but extremely important fragmentation probability at very low velocities. 20 centimeter per second was the average velocity in this experiment. So I'll come back to that number later. Another bouncing event.
Sorry, Jürgen.
Yeah.
Those fragmentations happen early when it was more porous, or later?
No, they happen rather late. So that's a good question, but they don't happen at the very beginning. I'll show you some porous fragmentation in a half an hour or so. Yes, I have half an hour left. Okay, bouncing with mass transfer. Remember the movie when the fragments came in from the top right and they hit the target and stuck by deep penetration? If the velocity is insufficient, not above the threshold I showed you before, the fragment comes, hits the target at some angle in that case, penetrates, however not deep enough, and then bounces off. Okay? Why don't we care? We do care because this guy, compared to that guy, which is copied in here, is much bigger, as you can see. So this took mass away, and typically a factor of 2 of its own mass. So it doubles its mass in a bouncing collision. And this is only valid if this large target aggregate is porous. So if you have some body, this can be either compact or porous, can take mass away from a porous target. Okay, going to fragmentation, and that means almost literally increasing the velocity from sub-meter per second or around a meter per second to above a meter per second for the material we used and the monomer sizes. Roughly above a meter per second, we do see fragmentation. So this is 2 aggregates colliding, and so they fragment at 2 meters per second in some big pieces. At 3 meters per second, the pieces get smaller. At 5 meters per second, they get even smaller. And the mass of the largest fragment can be expressed as a function of velocity, as well as the power distribution of the fragments. I'll show you a movie, because movies are always nice to see. So one fragment, this is microgravity in the lab, so this falls down in vacuum, this comes up in vacuum, so they don't feel the relative gravity. This is a perfect microgravity experiment in the lab, and you see what happens. They fragment. In that case, the largest fragments are very big still, but they produce a power law of small fragments. Okay, erosion. This is also a case that Stuart mentioned. You have a small particle hitting a large target, but now this is a very small particle. And we've done an experiment where we put a centimeter-sized high porosity aggregate vertically downward looking into a jet, a beam of little monodisperse micron-sized particles, and we could change the velocities from a few meters per second up to even 60 meters per second, and we found out that above 3.5 meters per second velocity, the target is eroded away. And the mass transfer, that is the mass, actually this fraction is the number of individual particles a projectile can hit out on top of its own mass, is usually quite big, a few, so 5 to 10. However, if you do these experiments continuously over several minutes or so, you see that this threshold increases dramatically to about 25 meters per second. What happens is that the porous target gets solidified, and it forms these solid bars here with holes in between. And this passivates itself for small impact velocities. No longer erosion takes place. It's a very complex process that we have not properly understood yet, I must admit. But I'll show you that it doesn't play a role in the model, unfortunately, because it's a nice process. But we have also covered that. And finally, the last fragmentation event, if you have a solid projectile hitting an equal-sized, a little bit bigger maybe, porous target at velocities of a few meters per second, you can see that this is the projectile, this is a glass bead hitting a highly porous dust aggregate, that after the collision, the dust aggregate was gone, was fragmenting, but part of the mass stuck to the projectile, and as a function of velocities, the volume increase was decreasing. So the higher the impact velocity, the fewer mass stuck to the projectile. And this can be given in a formula. Yes?
Could you go one back?
One back?
Yes.
Like this?
This is for one impact angle. I mean, just face.
Oh yeah, this is face on. This is
because
yeah.
it might change when you have random angles of refraction.
Good question. Absolutely. Yes. Right. I must agree. Okay. Good. Summing all this up, this is complex matter, I know. Thanks for not leaving the room. In our model, which I will show you, that is based on these 19 experiments and these 9 different processes, we derive threshold velocities for sticking, for bouncing, for fragmentation, for each of the 8 different regimes. We derive a porosity model for all the aggregates after the collision. We have a fragment mass distribution wherever it occurs, and we have a mass transfer model in the 2 of the processes. And to make things worse, we need a set of parameters to describe this. And these have all been kind of measured or approximated in the laboratory by experiments. So it's a whole set of like 15 or so different parameters describing the monomers as well as the aggregates. It's a very complex model. And this is the model. Okay, again, we have collisions between equal-sized particles, either porous or compact, and between aggregates of different mass, porous or compact. All 8 combinations are here. So little p is this collision, a small porous projectile hitting a large porous target is that collision, and this is the compact and compact large, and all the other combinations are here. Okay, let's zoom in the top 4. So porous and compact. Green color means sticking. S1 is the hit and stick with a threshold velocity of the inverse square root, mass dependence. This is this curve here. S1 is here, S1 is there, S1 is here. S2 is the hitting by surface effect, by compaction, for instance, that makes some kink here, changes the slope a little bit here as well, doesn't play a role in this. Then we have the simple bouncing with a compaction. B1 is here, there, and here. And in that case, we have an extended range of parameter for sticking by surface effects and some bouncing with mass transfer here. But this bouncing is actually red colored because it takes mass away from the large aggregate. And all this as a function of velocity from 10⁻⁴ meters per second to, well, to as big as it can get, to about 100 meters per second on the right end here, and a function of mass from the monomers at the bottom to about 100 grams in mass. So 100 grams is like this big. We're not covering the planetesimals in that plot because there's no empirical data available for meter-sized bodies. And you can see it looks complex, but it's kind of doable. And the bottom four look similar, but in detail they have some differences. They have some green vertical bars here, and I'll show you when I'll come to the simulations what this means. So this is the model, the 8 plots here. Okay, now comes the application, and we do the modeling part. That's the second paper submitted to ANA. Using a Monte Carlo code developed in Heidelberg and made much faster and better with the help of Chris Ormel. So it's based on the paper by Chom and Dullemont, 2008. And they have run some benchmark tests on their Monte Carlo code with a sum-kernel coagulation equation, which gives you an analytical solution. This is the curves, and the Monte Carlo results fit very nicely. And even the product kernel, which is a nasty one, because it's a runaway kernel, can be fitted very nicely. So we have some confidence in this code, and we trust that code in as far as we can plug in our physical model into that Monte Carlo code, because it has the advantage that it can not only treat mass and velocity, but it can treat porosity and fractality, if you like, and other properties that the particles bear as well. We've tested at one point at 1 AU in the midplane. So this is a very local simulation. So don't believe anything beyond, well, 100,000 or 1,000,000 years or so, because then things sediment and drift. But this is the first trial. 1 point in the midplane at 1 AU. And we applied 3 models. And we've heard about those models. The low density model by Fritjof Brouwer and co-workers. The minimum mass solar nebula model and the DASH model. That's the high density model. The plots of the surface density versus radial position are here, but we are only working at 1 AU in the midplane. So be cautious here. Okay, this is the relative velocities between the grains, equal sized and with a mass ratio of 100. In the model, included is Brownian motion, is sedimentation, although this does not displace particles, it's only the relative velocity, and an alpha turbulence with varying or variable alpha values. Standard is, I believe, 10 to minus 3. Is that right, Andras?
4.
4. Oh, sorry. Okay, so concentrate on minimum mass solar nebula model at 1 AU midplane again, and this is one of the main results. This is the time in years, so be careful. Whatever happens right of these lines where sedimentation and drift timescales become important. This is the mass distribution given by color of the aggregates as a function of time, and we see some steady increase at the beginning. So the first 100 years it goes almost with a power law, then the slope of this power law, whatever law it is, changes. It goes up to about 10 to minus 4 or 5 grams. Then it's getting slower again up, and then some magical thing happens within an extremely short time scale. You can see that here. It's interestingly the time scale that Stuart Weidenschilling showed us, a few thousand orbits or so. Things change dramatically up to a fraction of a large fraction of a gram, and then falls again. And then due to this little fragmentation probability in bouncing, the whole thing goes back in mass again, and then somehow stabilizes at control masses. So this is the mass, and the distribution of mass stays rather narrow. It's not the process that Stuart Weidenschilling has calculated to be important in his process, the addition of small particles to large ones. There are no small particles after about 100 years. This is all black. The same, this little kink here, this magical thing happening, is due to the transition. This is the minimum mass solar nebula model, velocity versus mass, transition from Epstein to Stokes regime. So believe it or not. So, of course, this is not as deep as in this as a simple model, but it has some influence, and you can see that. So one has to be careful. Okay, next plot is the porosity plot. So this is the enlargement parameter. The inverse of that is the filling factor. So we start with the monomers. They are by definition compact. In the first 100 years, it gets very, very fluffy. So enlargement parameter is 20. So that means 95% porosity. And then due to the bouncing with compaction, the porosity goes down again. And then it stabilizes at rather dense material packing. And from the 9 processes we've investigated in the paper 1, only 4 are important. That's a disappointment if you do a lot of work in the laboratory. But this is also a learning curve. So I'll show you a little later that from the Monte Carlo simulations, we do learn which experiments are interesting to perform next. So we won't do experiments on S3 and S4 and all these Fs here, but we will concentrate on these things. So only hit and stick in the beginning. So this is time and this is the process. Hit and stick in the beginning, then continued by the sticking by surface effects all over the time, and at the same time the bouncing with compaction sets in. This is also very, very important all over the time, and some bouncing with mass transfer has also some importance. Not a single fragmentation event happening here. Okay, this is the movie. What happens? Time is running here. This is the mass of the grains, and this is the enlargement parameter, so the porosity, if you like. Mass grows, porosity grows as well. Time goes on logarithmically, so you'll see that speeds up soon. So this is the mass distribution, it's the width here, and the porosity distribution, it's the height here. So this goes on very, very fast, mass gain. And now this transition from Epstein to Stokes will happen soon, now. And now the bouncing with compaction comes. So things get compact, and with a probability of 10 to the minus 4, there's some fragmentation. So mass goes back again. And then it stabilizes. So it's a hidden fragmentation, of course. It's a fragmentation and recoagulation that stabilizes the thing on this point. So at masses of 10 to the minus 3 grams, millimeter-sized particles with a small enlargement parameter. So they are not so porous.
Can you explain a bit what the effect is when you transition to Stokes drag? I'm guessing the velocities become a bit bigger, the stopping time is longer than it would have been? Or
can you rephrase your...
What's responsible for the effect when you transition to Stokes drag?
It's the Knudsen number.
Is it making the velocities larger? Or
It does, yes. Oops, here. This is velocity, and by changing the mass a little bit, you go from the Epstein to the Knudsen regime, and the velocity jumps up by a factor.
Jürgen, what's the inner scale of your turbulence, and is that a factor in there?
Antosh, inner scale of the turbulence. That's a pure alpha description all over the place. So this is a local simulation. So this is...
But there's some scale at which the stopping time of the particles equals the time scale of the smallest eddies, and that could be a significant transition in the behavior.
Yeah, I don't think that is included here. Okay.
That is included.
That is, yeah, we have all the experts in the audience. Okay, this is the result of, you saw the movie, and now let's concentrate. These 8 plots is the model, and this is where the particles really are. And let's concentrate on the top 4 panels, because there's not so many here. So where the red color is, things happen. The major growth is only possible in the, if we go back, is only possible in the green regimes here. Of course, this lower left corner is fine, but going away from the lower left corner, only this green regime is left over, and some bars here. So this is where the growth happens. Different sized particles, both porous. A small porous projectile and a large porous aggregate is where growth can only happen. However, our growth process limits the size distribution width such that this dies out after some time. It becomes monodisperse. So these things grow and reach here, and then they bounce and become more compact, like here. And they go from here to there. Equal-sized, compact particles bouncing, and then they fragment with a low fragmentation probability, and they go back here, and this is where everything ends. Oops. Okay, so we've tested a few things. Turbulence parameters, so the values I've just shown is 10 to minus 4, the three models, the Prower et al. Low density model, and the minimum mass and the Dash model, high density, as a function of turbulence parameter. There's some dependence, nothing that is very systematic, but the overall dependence is rather weak. So the influence of turbulence might not be that important. However, at a higher turbulence velocity, alpha 10 to minus 3, we do find some additional fragmentation events. But this does not trigger a fragmentation coagulation cycle. And another important parameter in our calculations is the critical mass ratio. Where is the transition from equal sized to different sized? And the nominal value is 100, but we've also tried 10 or 1,000, and you do see some changes. Not in the two higher density models, not so much at least, but in the Prower et al. Model, there are differences. So it is dependent on this parameter, and that is a duty for us in the lab to find out where the parameter really is. Okay, let's conclude and look out to what we will be doing in the next future. What we've seen is that growth stops at typically millimeters. If you reduce the fragmentation, then centimeter-sized particles, and the stopping is due to the onset of bouncing. There's no growth path that the particles really go, although there are some, but the particles don't go these. So, and we call this the bouncing barrier. So we have a fragmentation barrier, we have a meter-sized barrier. However, before both can be reached, they stop at the bouncing barrier, I believe. The fragmentation regime is only reached for the higher turbulences that we investigated, but that does not lead to a new growth mode. The mass distribution at all times stays rather narrow. We don't find this bimodal distribution that Stuart has shown. Obviously, it's the different models that result in different size distributions, which is, of course, something to be thinking about. And the retention of small grains, as observed in the atmospheres of these disks, is not possible with that model. So these things are happening deep inside the disks, absolutely unobservable. That's a good thing. Maybe with ALMA a little later, or super ALMA after that. But there's no process that we can see that produces small grains up in the atmosphere. And compaction is of utmost importance. So the bouncing collisions are of utmost importance. The final porosity is only like 60 to 70%. That's not so much. It sounds a lot, but if you take some powder and pick up some aggregates from any powder, they have about that much porosity. Okay. The main questions that we ask ourselves are, at which mass ratio is the boundary between this left column, similar size collision, and right column, different size collision? We have to find that out. Is that a sharp transition, as we have modeled in our binary model, or is this a smooth transition? And the same question can be asked in the boundary between porous and compact, so the first row and the second. Is it a sharp transition or a smooth one? We set it at 60% porosity, arbitrarily, without better knowledge. And so that needs to be investigated in the near future. The good thing is that the results of the Monte Carlo simulations show us unambiguously from these simulations at which mass of projectile and target, at which porosities of projectile and target, at which velocities things are happening. So we can go to the lab and make an experiment with M1, M2, Phi1, Phi2, and V. And if it turns out to be different to what we had interpolated from our previous experiments, then we have to rerun the model, of course, and do a new experiment. So it's a cycle as in the model of Stuart-Weidenschilling also. So, and we do have to extend, of course, our local simulation to more a global one. Okay, two examples of what we've already learned. On this upper right panel, small porous to colliding with a large porous particle, we have this striped region. And this is a transition between sticking by surface effects and bouncing with mass transfer. We found in this velocity region by experiments, we found both things happening. So we set a probability here. And it is not important whether there's a probability or a sharp transition, both modeled here. It basically leads to the same mass versus time behavior. So this is an unimportant process. We don't have to care about that very much. An important process is the fragmentation probability. This all happens here when two more or less compact particles collide and bounce. Things fragment, and so the mass goes down with time. So if we have do not have a fragmentation probability, we follow this curve and the things stay big. So the mass is like a gram here or so a centimeter particle. And with a 10 to the minus 5, 4, and 3 fragmentation probability, things go down and kind of equilibrate at a millimeter size range. So this is an extremely important parameter we have to investigate, and we've just started a new experiment. These are very new data from last week. So this is a porous particle, and now this falls down at 50 centimeters per second on the target. So the target's a bit faster. It's in rest when it's hit. So this is number 3, I think. Number 4, we are not waiting 10,000 collisions now, but only like 5 or 6. Okay, you see, it lost one piece, and it goes on. So the previous experiments with the 10 to the minus 4 fragmentation probability were done at a velocity of 20 centimeters per second. This is 50 centimeters per second. So just a little bit higher, and things change dramatically. And this is not included in the model yet, but it will be. So it's grinding down as we continue. I've only got 5 minutes. So I continue. The next experiments under investigation are marked by the ellipsis here. So we are taking the results of the simulations and look into what we can do. And I believe the next is, yes, next is this. This is our latest experiment also with the fragmentation set aside. This is a free fall experiment in our little new 1.5 meter drop tower. We have built ourselves a little drop tower in the lab. It's 1.5 meter free fall, and it will repeat hopefully. Okay, so it's a 2 centimeter dust particle and another 2 centimeter dust particle hitting each other at 1.7 centimeters per second. This is the lowest velocity I've ever been able to achieve in the lab. Filling factor is 48% of both particles, and we have just started to investigate these collisions. They are all bouncing. So even at 1 centimeter or 2 centimeters per second, we didn't find sticking. So we are in the bouncing regime, that's fine. So it is compact on compact, equal size. Centimeter is gram, so we are about here with the experiment in this corner. This is not a valid corner, but we go down in size. It's a bit more complicated. Okay, where do we stand in terms of completeness of the experimental investigation? So we will never be complete, but just to quantify the completeness, I've put some bars here. This is the size of the dust aggregate consisting of micron-sized particles. So from a micron to about 10 centimeters, that's all doable in the lab. Anything from 10 centimeters onward is, of course, impossible to do in the lab. In terms of mass ratio between projectile and target, you can do things between very similar particles, that's the 1, or you can do collisions between small and large ones, that's the 0. So we're somewhere in between. This white region is what is of interest, what we will do next. Collision velocities, anything is possible from 10 to minus 4 meters per second, then for small particles in the Brownian motion, that's all done, to 1 centimeter per second, I've just shown you, to up to 100 meters per second, it's all no problem. So the velocity is the easiest thing to do. Porosities, we have, of course, easy is to make compact particles. Extremely porous particles, like 95% porosity and millimeter size, is not what we can do at the moment. So this is our white space here, still left over, and the biggest white space is the material. So we've done the silicates, if you like, with SiO2, and I believe it doesn't matter very much whether you mix in a little magnesium or iron, so the van der Waals force would not change very much, and 300 K. Temperature is also an option, so you can do silicates at 1500 K, just under the condensation temperature, as well as oxides and metals further in the solar nebula, or organics in the asteroid belt, or ices. And many people do believe that icy particles are more sticky because the van der Waals force is a factor of 10 higher or so. That might be the case or might not, and we have to do the investigation. So I cannot answer any question about ices because I don't know it. So we can run our simulation now with a shift in sticking velocity, a factor of 10 higher, and see what happens, but this would all be hypothetical, I think. Okay, so to the last question, last minute or so, can there be any growth beyond centimeter? So that's the maximum size we were able to reach in our simulation based on the experiments. Okay, this is the way we go now, and then we end up in the bouncing here and go down. So there's two ways to grow bigger. Infinitely big is mass goes up here, and at the velocities that Stuart Weidenschilling showed us, like meters per second and higher, the only green range, yeah, you can see, that goes to the right end of the plot is that one. And this is a compact target, fine, because we produce the compact targets here, and a porous projectile, much smaller than that. So we need a source of small particles, either the monomers or small aggregates, in order to get here. That's one thing. Or if you take the combined motion of many particles into account and believe that the velocities then are decreased, as Stuart has just shown us, decreased to a few meters per second, there's two more ways to go up to large sizes. However, our model, based on this experimental based model, does not predict that this way is gone. So we need a source of small particles, or we need to reduce our model velocities, taking into account the cumulative motion of a layer of particles. That might end then in the increase of mass. But this needs to be seen in future calculations. Okay, that's my story. Thank you very much. I want you to acknowledge our sponsors here, shown with labels. And thank you for your patience with me.
Questions? Stuart?
Jürgen, I would point out that at least in a non-turbulent nebula, you would have a steady source of small aggregates being supplied as things rain down to the central plane. All the simulations you showed had some non-zero alpha, even though you had varied that for some range. Was the only source of relative velocities in those simulations the turbulent velocities rather than differential settling and radial?
Those three, yes. Brownian motion, differential settling, and turbulence.
They were all in there.
They were all in there, yes.
Okay. I would suggest that it might be an interesting end member calculation if you could do it for alpha equals 0 when you had only the differential drift motions, at least until you get down to where collective effects become important.
Yeah. I think that's on our list as well. Thank you.
Nader?
Jürgen, maybe you already mentioned this. In your growth movie, did you investigate at what stage the porosity of the object changes?
Yes.
Okay.
So it was taken into account at any stage.
Okay.
So all the processes do involve some changes in porosity, all taken into account.
Is there any specific time that the porosity may change and the object become actually compact? Do you see any relation, or?
Maybe I go back. I think here it can be seen. So this is the porosity, if you like. It goes up while things, if we go to the, okay, it goes up to a few thousand years, and we have the hit and stick, and the sticking through surface effects and some bouncing. So until this time, the porosity goes up, and beyond this time, when the hit and stick ends, things bouncing with compaction takes over. Oops. Porosity goes down again. So that's the major effect.
So is that 1,000 years something that you see in all your simulations? Is it something that you can say porosity normally changes around that time?
Oh, absolutely, because that up to here, there's only sticking. So that's a natural growth time scale, the same time scale as Stuart showed. That's an absolutely natural time scale, so can not do anything about that.
Doug, if you were to try to compare, let's say, with chondrules, and which has a limited range of particle sizes. Now, I assume that there are some chondrules that the matrix is very limited, the matrix material. So how do you think those things got together?
Yeah, that's a good question. I have thought about that myself. And
Can you repeat the question?
The question is, we end up at millimeter sizes, chondrules, and there's evidence from meteorites that there are some chondrites that contain like 80% or so in mass of chondrules and only 20% of cement in terms of matrix. And I don't believe that this is a cement in the building business sense. So the question was, how do I envision this mass of chondrules comes together and sticks together? I have no idea. The only way I can envision it at the moment is by gravitational attraction, mutual gravitational attraction. See many of those. So some instability brings together all these chondrule precursors or chondrules, and then things grow big enough to be held together by gravity.
But isn't that kind of dangerous also, because if gravity came in too early, then the CAIs in them are sufficiently hot, and then you will release so much internal heat to differentiate the chondrules, and you won't have chondrules.
Yeah, right. That's definitely a concern. However, let's go back one. We are staying at chondrule sizes for basically infinity here. So we can wait until gravity sets in. So you theorists have to tell us how gravity comes in at a later stage and not now. So we are, I would say, a scenario that I can envision is we produce the precursors of chondrules, and at some time later, millions of years later, these transient magic events come that melt the chondrules. It's just fine because we're sitting here and waiting. And then the gravitational instability comes. So it might be hidden in the transition between dust and chondrule that the gravitational instability is triggered. That's a possibility. And then the CAIs will not be too hot.
Yeah, that was very interesting. I just have one question. Are you planning to do some more lab experiments with different material than silicon dioxide?
Yes, we do. We are setting up an experiment. It is almost finished. Maybe we're a half year before the first experiment can be done to do experiments at high temperatures. So any temperature between room and 1500 will be possible. It will be limited to about 1 meter per second and millimeter particles, so restricted somehow, but we'll investigate how silicates behave at high temperatures as well as other materials at any temperature between room and higher. And we are setting up experiments with ICES. So both ends will be done. Organics, I don't dare working with. I have no idea how the organics in the solar nebula looked, what they were composed of. So whatever you do in organics, you do it wrong, I think.
Do you expect the results to be very different for ice, for example?
For ice, I don't expect. I think ice at 100K is a rock. I don't believe it makes a major difference. Organics, of course, can be sticky. Yes, anybody knows. I expect some differences at high temperatures. If you go with silicates to high temperatures, so freshly condensed, and within a few thousand years nothing changes in terms of temperature, that might change the viscosity of the materials. Sintering becomes an important process, so that's what we want to investigate.
Richard?
Jürgen, do these models include anything other than two-body effects, for example, three-body or four-body type effects?
Absolutely not.
I mean, what do the statistics say regarding the number density of particles that you have as to whether or not three-body effects could be coming?
Oh, no, no.
Definitely not.
Absolutely not, no.
Yeah, I wanted to say a few words. I think this problem that if we bring the contours together too quickly, we differentiate the planetesimal is a circular argument, because when we look at a chondrite, in order to bring the contours together to form the chondrite, we need to have the contours. And it's a fact, as Mathieu showed yesterday, that these contours form late somehow for some reason, with a delay of a couple of millions of years. So when you bring them together, then a lot of aluminum has already gone away. It might be possible that there was an early generation of contours and that you brought it together very early and then you differentiated that planetesimal. You call it now an iron meteorite and you don't see the individual contours anymore.
Right.
So I think this is a circular argument and that cannot be used to say that this process
it's just
of gravitational
question of
collection
putting
can
together
work.
the chondrites. And how do you put it together in a way that that you don't have a lot of matrix?
Oh yeah, that's another issue.
Yeah. The stickiness is reduced once you have millimeter particles. There's no doubt about that. Unless you have a completely different material or higher temperatures, everything is like honey or so, then it might stick. We haven't investigated that yet. So that might be possible.
I was just going to say that there have been some experiment done by Bud Bridges with some methanol, a small amount of methanol.
Ice.
It's comparable to what you see in the comets, and they are like honey.
Yeah, but that was methanol snow, if I remember correctly.
No, but this is not yet published.
Oh, that's newer things.
Yeah.
Okay. Ah, yeah.
Yeah, as far as organics, you know that organics in meteorites are very similar to terrestrial kerogen. This is something you can try. I mean, it's not that poorly known as we want.
Okay. Yes, if I would love to speak to you about that. And is that dangerous material?
I don't think so. That's what
Very
you make.
lot of plane.
That's what you make oil from.
Andrew?
Yeah, so would you mind showing the one again with the three different alpha values and the three different models? I think it's, I mean, one thing that's really interesting is it looked like in the low density model that gets very small sizes, that's presumably a stopping time effect that they decouple from the low density gas. Whereas the gas density doesn't seem to be a big difference in the upper two models.
Right.
That's one interesting thing to understand is when is the dominant effect.
Yes, and
time and when
and
is
the
it-
result is that the relative velocities here are too high. Yeah.
But yeah, and I'd be curious to see how that behavior scales, say, with radial distance from the star, where obviously the size, stopping time, relation changes.
Yeah, we're working on that.
When I looked at the micrographs in the presentation yesterday on meteorites, the sort of thing I see is a matrix in there, and it seems to me as though that says something about surface properties and surface, the elements that you're trying to put together. I see angular fragments. I see a size distribution.
Absolutely right.
I don't think any of those things are in any of the experiments that you do, and I would wonder which of those you think are most important. And then a corollary question would be: have you ever taken, after one of your experiments, and done micrographs or taken slices through them to see what the mechanical constitution of the elements are?
To answer your first question, we did experiments with different materials. So I only showed you the bulk of the experiments. That was done with these SiO2 spheres. We have irregular particles, SiO2 again, irregular particles from 0.1 to 10 microns. And we can make our very high porosity samples with those. Qualitatively, there's no difference. Velocity shift may shift by a factor of 2 or 3 or so. Usually those aggregates are more fragile, so they are much harder to produce. However, this is, I think, a relatively minor effect. Of course, there's no rolling if you have angular particles, so that this needs to be done. But and we are thinking about an experiment to test a huge set of materials and and defining a standard experiment, how to find out how things, which material size distributions and shapes are better or worse. But we haven't done that experiment yet. But we have probed into little diamonds as well, and silicon carbide particles, and they don't show a major variation in stickiness, kind of, in fragmentation thresholds. What we have done in our experiments is we sometimes take electron micrographs and look at our particles after collisions. Usually the particles, individual particles, are not harmed. The velocities are meter per second, so that nothing changes. What we have recently done is we have done X-ray tomography of the particles to investigate the compaction, densification, and that led to some of the results I showed you on compaction.
The last question, Jack.
At the risk of bringing up the snow line's importance, you talked about 1,000 degrees, maybe that makes sticking more. You said ice at 100 degrees you think will be like rock. But have you thought anything about ice near the snow line and whether that may be more important than the amount of solids, just the stickiness of solids near the snow line?
As far as I know, but you might correct me, is that ice at the snow line is 140 K? 160, okay. We have done solid ice on solid ice in the millimeter size regime at 150 or so. And that was hard as a rock, so.
Add some ammonia.
Okay. Remind me, and then we have another parabolic flight on ice collisions in March. We might want to do that. Yeah. So I have very limited experience with ices, but I do have some, and all they tell me is that at around 150 K or so, it's still hard as a rock. Not only at 100, yeah.
Okay, we have a coffee break now until 11:30. Let's thank Jürgen again for